In this video, we describe how we can solubilize insoluble salts by the formation of complex ions. Our starting point is a discussion of what a complex ion is, so let's get started with that. It turns out that there's many metal centers that are very good electron acceptors. So for example, aluminum 3+ has a great tendency to accept pairs of electrons from nearby molecules. Okay, so a substance that has that tendency to be able to accept electrons or pairs of electrons is what we call a Lewis acid. Okay, so what type of molecules can donate electrons to these metal centers? Well, for example, water. When you think about it, this is the Lewis dot structure of water. You actually have lone electron pairs in that water molecule that can act as a Lewis base. All right, so then what will happen is that this Lewis base will interact with the Lewis acid, which is your aluminum center, to generate quite stable complexes, right? So it's very common to find complexes like this. Aluminum with 6 water molecules, 3+. And this is what we call a complex ion. And we will discuss the nomenclature and properties of those complex ions in a few videos. All right, our goal here in this video is to explain how you can utilize these complex ions to solubilize salts that are highly insoluble. Okay, so let's take the example of silver chloride, yes. So we can take silver chloride, which is a solid, and look at the solubility product. Silver ions, and then chloride ions. This KSP is quite small, 1.6, 10 to the minus 10, right? So highly insoluble salt. Now, what we want to do is try to improve the solubility. What we want to do is try to take as many possible silver ions out of that insoluble silver chloride to be able to use them in a different application. So the idea is that, well, because silver plus is a metal center that is a good Lewis acid, then we can try to form a complex ions with a molecule that has electron pairs that can be donated, a Lewis base, and then if the formation constant for that complex ion is very high, if that is very stable, then we might be able to sequester, to solubilize that silver chloride and sequester those silver ions into the complex ion with that base. All right, so it turns out that silver plus forms really stable complex ions with ammonia. And as you know, ammonia has a lone pair. When you draw the Lewis dot structure of ammonia, it's something like this. Right, so that acts as a Lewis base, which can interact quite strongly with that silver plus Lewis acid, and then be able to increase the solubility of the silver chloride. Okay, the reaction that actually takes place is like this. Silver plus with 2 molecules of ammonia generates this complex ion. That's the full complex ion plus, and then the formation constant for this complex ion is very, very large. We're going to call this K sub F for formation constant of the complex ion. This number is 1.7, 10 to the 7. All right, so this is what we're trying to do then. Notice that silver chloride by itself is very insoluble, right? The amount of silver ions that you get in solution is very, very small. However, these ions can actually react very quickly and very strongly with those ammonia molecules to generate this complex ion, and that is very favorable, right? That is very displaced to the right. So then the idea is to try to solubilize the silver chloride by reacting this silver plus with something that is going to lead to a very stable complex ion, which is that one. Right, so then let's try to do a numerical example to see exactly how this works. Right, so the idea is to calculate the solubility of silver chloride in a solution that is an aqueous solution of 1 molar ammonia. Right, so our concentration of ammonia will be 1.00 molar. Our goal is to calculate the solubility of silver chloride. Right, so what we actually do here is we add up these 2 reactions to come up with the overall process. And the overall process is going to be as follows. Notice that silver ions are both in reagents and in products, so they're going to be canceling out. So then our overall process will be silver chloride, okay, plus 2 molecules of ammonia is going to lead to this complex ion, which is soluble, and then chloride ions. And it turns out that the equilibrium constant for that particular process, the overall, is simply going to be the product of those two. We are not going to see how you can calculate the equilibrium constant of the overall reaction as the product of the individual equilibrium constants for the two processes, but that's something that you can do on your own, and it's not difficult at all. All right, so notice that then what will happen is that the value of K, which is the product of those two, that is going to be equal to 2.7 10 to the minus 3. And notice that this is going to be equal to the concentration of your complex ion multiplied by the concentration of chloride over the concentration of ammonia squared. Okay? Alright, so the question is, how do we solve this? What we're trying to find here is the solubility of silver chloride. Notice that the solubility of silver chloride is going to be given by the concentration of chloride ions that you have in solution. Okay? In this process, we can actually assume that most of the silver will actually be forming part of the complex ion, and there will be very little silver left in solution. So what will happen is that the amount of chloride in solution and the amount of the complex ion in solution, they're going to be the same by stoichiometry, right? So the only thing that we actually have left over here is well, what is the amount of ammonia left over once equilibrium is reached? Okay, to actually do this, what we're going to do is set up here an ice diagram to be able to find what the solubility is. Right, we can't forget about silver chloride because that is a solid and does not participate into the equilibrium constant. So then what we have to track here is what is the ice diagram for the other species that are intervening in my equilibrium constant. NH3 2 plus and then chloride minus. Alright, so that is going to be your ice diagram. Initially the concentration of ammonia is going to be 1 molar. Okay, that is by design. Initially we do not have any complex ion, and initially we might have a little bit of chloride, okay, and that is because you actually get a little bit from here, but that turns out to be a very negligible concentration, so we're actually going to neglect it entirely. Okay, then the change would be as follows. Notice that the stoichiometry is 2 molecules of ammonia to each one of these, so the reaction will be displaced to the right, minus 2x to xx. And X is exactly the solubility of silver chloride. Okay, notice that however much silver chloride dissolves is going to result as chloride ions in solution. So we can use that concentration of chloride ions to determine exactly the solubility of silver chloride. Okay, so at equilibrium we will have 1.00 minus 2x, xx, which means now that if now we take these equilibrium concentrations and take them back to the equilibrium constant, what we will get here is x squared over 1.00 minus x squared. Alright, so this is a simple equation to solve because you have a perfect square. Okay, you can take this, take the square root, you can take the square root of that, and then you can take the square root of this, and that's essentially what you have right here. Okay? Alright, so solving for that, you get to a solubility of 4.7 10 to the minus 2 molar. Okay, and this solubility, when in a 1 molar concentration of ammonia, has to be compared to the solubility that you would get if you were in pure water, so no ammonia. The solubility in pure water is much, much smaller. Okay, that solubility in pure water versus the solubility in ammonia is equal to 1.3 10 to the minus 5. Alright, so by simply adding ammonia, which leads to the formation of this very stable complex ion, you're increasing the solubility of silver chloride with respect to pure water by a factor of about 3,000. Okay, so this is a great way to solubilize insoluble salts. Okay, so to summarize this video, what we have done is to introduce the concept of a complex ion And then we have seen how you can use the formation of that complex ion to improve the solubility of highly insoluble salts.